We're continuing with the river and stream geomorphology from chapter 6, physiography of rivers and streams. And we were just talking about how rivers naturally meander across the landscape. And they do so by making oxbows, which then eventually get cut off, and it changes the channel. And this leads to a lot of heterogeneity in the channel. This next image is of the Grand Canyon, and it shows another type of heterogeneity. And that is where we have a side channel coming into the main channel. And that material that comes in that side channel, in a sense, sort of dams up the river, the Colorado River. So behind that, there's a nice big slow pool, but then it leads to an elevation drop. And so this is what the big rapids are that people love to run. And rivers, they're related to oftentimes to these side channels bringing in material and causing this heterogeneity in the stream channel.
What do you mean by heterogeneity? Like in the water? Like what's in the water or the shape?
Yeah, so I guess, yeah, that's a really good question. What I mean by heterogeneity is different types of conditions in the river. And this might be important, say, if you are a invertebrate that likes fast water, you would be in the rapid area. If you're one that can't swim very well, maybe you'd be in the pool, right? And so it makes for a wider variety of types of habitats in the river or stream. Good question, thank you. This is an image that was from LiDAR, a laser remote sensed elevation map of the Willamette River in Oregon, and it is flowing from the bottom to the top. It's a river that flows from the Willamette Valley, goes from Eugene to Portland in Oregon. But what this fine scale elevation map does is it gives you an idea of how this river has moved across the landscape over time. And I just thought this is a really striking image that showed that. You can see where there's old river channels here, here, you know, over here, out here, all kinds of different movements. And you can imagine that, and this helps you imagine how this river's moved back and forth across its floodplain over time. Again, creating heterogeneity in habitats. So some of these might be wetlands or remaining oxbow lakes or something like that. You can also see that there's some actual development where it's channelized right here, and that kind of sticks out in this particular image. And then that same river, we can look at what's happened to it over time in terms of complexity. And so in 1850, the image on the left shows the complexity that was in the channel. And we see it got braided, it had multiple different pathways that went through and sort of dead ends and such that are semi-connected. And in 1895, it was similar. By the 1930s, it started simplifying, but because of human activities. And by 1995, you can see there's a substantially simpler stream channel than there was in the 30s. And this is related to management, putting in levees, channelizing, and also the Army Corps of Engineers spent a lot of time simplifying and opening channels so people could move up and down the river as well as for transportation. And the part of that was pulling out trees, dead trees, snags from the river that would impede the boat traffic. And this is the number of snags that were removed from the river each year by years from 1870 to 1950. And we see that at the peak in around early 1900s, they were removing thousands of pieces of wood from this river. After 1950, that it was not used for transportation very much, mostly just some recreation, and so that they stopped removing the snags. So this is also a place where they decrease the amount of heterogeneity in the channel. Sorry, my air conditioner's loud. I needed to turn that off. All right, and we're moving to the question of the day here. And would like you to type your answers in there. So we've got a lot of really good answers here. Yeah, everybody pretty much got that, you know, a passive way to manage would be to just let the river wander and go wherever it wants, right? So this is not, you know, not going to work in Kansas City and St. Louis or, you know, Portland, the river, because it's all built up and you're just not going to have that happen. But areas outside where there's more agriculture or something, maybe you could let it go. There'd certainly be more space for recreation, and you could have agriculture with the understanding that it's possible that you'd have flooding that would sometimes interfere with the agriculture. The Nile in Egypt is one that was naturally wandering and flooded every year for much of human habitation history there. And the floods would bring in fairly rich soil and deposit it and keep then when the floods went away, they could plant crops and they would grow well in that rich land. And so that was a sort of a naturally managed system that served humanity well. Now that they're controlling floods and sediments and there's a large reservoir at the upstream, the delta of the Nile is disappearing because the sediment's not reaching it, and a lot of the farmland that was there is going away. So that's a situation where dams actually caused some of the problems as well. And now we can talk about the kinds of things that are dissolved in river water. And this is a global assessment, and they look at the chemistry of the really just most of the largest rivers, the Congo, the Nile, the Amazon, the Ganges, the Yellow River, some of the really big ones in the world. And they are integrating over large spatial areas. And you can get from history, you can get the natural concentration, or sometimes there's ways to back calculate that. And the current concentration of calcium, magnesium, sodium, potassium chloride, sulfate, nitrogen, and phosphorus. And we see that many of these things are increasing substantially. So the difference between the natural and the current is under the pollution column, and the percent increase of these materials is in the last. And we see that many of these are increasing. So why do you think sodium and chloride are increasing that much? Anybody have any suggestions?
Maybe when they salt roads and it runs off into rivers.
Yeah, we're putting a lot of salts in, and then also we may be drying things a little bit more, so it's concentrating it more, right? So salinization is a real problem in, say, California, where they've irrigated and the evaporation then leads salt formation. Then when it finally washes out, it makes it salty. We eat more salt than ever in human history. Chances are it's a low amount, you know, relative to the total fluxes. It's probably a fairly small one. Sulfate is both from atmospheric deposition, and we'll talk about that when we talk to acid rain, but also fertilization, fertilizer. There's a lot of sulfate in fertilizers. And the 30 and 50% increases in nitrogen and phosphorus we'll get at, those are due to fertilizer from cropland for the most part. We're really putting a lot of nitrogen and phosphorus, and we'll again talk about that later. So we see we have global effects on the chemistry of rivers. And we can talk about how the materials might move in streams when you put them in there. And on this is a release of salt at 0 meters and chloride and 100 meters downstream. and it was released over 30 minutes at the 0 point, and then measured 100 meters downstream over time. So we see that whereas it was just an on-off release at 0 meters, by the time you get down 100 meters, it started to spread out. Some of it moved faster. So this is in what's the fastest portion of a stream called? Anybody remember that word?
Thalweg.
Good. Yes, one of my favorite words, the Thalweg. Yay. Good, Jaden. But also there's some hang up here, right? There's some that really takes a long time to come back out of the system. And this is maybe in a pool. And there's also, I mentioned the hypereic zone. If you remember, we talked about, I'll put it, see, oh, there it is. We talked about the fact that there might be places where there's exchange with groundwater, gravel bars where the water flows through more slowly. So the salt could have been released here, and some of it could have ended up getting kind of stuck up here and slowly coming back out again. We can use this type of plot then to actually model what the amount of hypereic area is. And we can also get the discharge from this by the amount of dilution there is, and we can get the average velocity. Hypereic, there it is spelled. It's a weird word. That's not my favorite word. I don't know why, but it's the one that I always have trouble with. I had trouble with from the beginning. Okay, the other thing you can think about is velocity, water velocity, and how much things can move. When we were at Kings Creek, I talked about how with a really large flood, entire gravel bars were moving, large rocks and cobbles could be moved around. So it makes sense that at higher velocities you get erosion, you get movement of materials. But different particles react differently. So at really high velocity, everything's moving, right? But at low velocity, you're not going to have much transport of rubble, boulders, maybe a little bit of gravel, probably not. It's sedimenting, it's staying on the bottom, but it's being transported. This, like even at fairly low velocities, clay can be transported. One of the things that can happen though is really high velocities, clays can get pushed down, small particles can get pushed in and compacted into the bottom. And this is a plot of two velocities on the percent of solids at different sizes. And so the circles are a lower velocity and the triangles are at a higher velocity, at about 4 times higher velocity. And we see that the highest percentage of particles are a millimeter or less at the low flow condition. But at the higher flow condition, these larger particles start to dominate. So you can get movement of larger materials. So this just quantifies what we all know. When it floods, the water gets muddy. And when it really floods, rocks and all kinds of big things can move. And I'm going to talk about environmental and extreme environmental impact on streams in the Adirondacks in eastern United States. And this is mountaintop coal mining. And what they do in this situation is they just strip the tops of mountains off to dig out the coal. And you can kind of see a layer of coal here, down here, and they've cut this off. And what they do at the top of the mountain is they just throw it over the side. And so they just completely fill the channels. And that was something that was regulated starting to be more regulated in the Obama administration, but they've rolled back these protections. This also has big health impacts on the people that live in the communities downstream because a lot of sediment moves into the channels and the erosion moves the materials out. And some of it's fairly toxic stuff. So this is environmental impact. If you ever are in a airplane again, flying across to the East Coast and look out the window, you'll see very large areas that have been subjected to this. And then we're going to go back to scale. So we've got temporal change on the x-axis and spatial scale on the y-axis. And we're talking about up to continents, and we're talking about, you know, 10 to 6 years, so multiple centuries, and down to, you know, seconds, and the sizes of microbes. And again, this is what another aspect of heterogeneity. We can think of it as another aspect of heterogeneity, and linking the physical with the biological actions. So the very fine particles here might be clay, and we have rocks and wood that are more like in the range of the scale's not there, but this is meters. And then we get up into pools and riffles, and then a bunch of those together would be a reach. Maybe between the entire length that's second order might be a section of stream before it turns into third, or became a second order from first order. And then watersheds can go all the way up to the size of continents. And then how organisms overlay on that. Microbes are operating at this very finest scale, macroinvertebrates and this rocks and wood kind of things. Fish overlap. Detritus can really have the dead organic material can have a really large span. It can be as small as a microbe, but as large as a large log, right? So it can be quite big. Some of the logs and trees take hundreds of years to decompose once they're in the bank, so they have really long turnover times. And then there's ecosystem engineers. Gretchen, you raised your hand.
Maybe you're getting to it. I was wondering why alligators and hippos are ecosystem engineers.
Oh yeah, I was just going to get to that.
Okay, sorry.
And I'll answer Emma's question. She asked, is temporal time? Yes, temporal is time. So like temporary is a pause, right? That's the same root there. Yeah, so beavers is obvious. Beavers make dams. Actually, they don't in this part of the world very much. They tend to dig holes in the sides and of rivers, and don't dam up streams as much. Although some of they can. And we talked about that. If you go out to Tuttle Creek spillway, there's a nice complex of beaver dams. But they can basically allow sediment to accumulate in entire river valleys and really change the habitat, make a lot of heterogeneity, right? Make wetlands. When the beaver dam goes and the stream goes somewhere else, then there's going to be a wet area that's flat and has rich sediments for riparian plants to grow in. Alligators are actually will dig out pools and say for the Everglades, they'll actually dig out pools to keep water in when it gets droughty, and so they'll change the landscape. And hippopotamus also do that. They are also bringing a lot of material into rivers from outside because they go onto the terrestrial habitat and graze, as do engineers, beavers, and pull materials into the streams, and so they can, and rivers, they can change the chemical makeup, and then their trails in and out can cause sediment to come in as well.